everybody. I'd like to thank Marco Muñoz to be here. And Marco was here in 2017, I think, to the postdoc. I think
2016, yes.
16 and 2007.
Mm-hmm.
Yes, that's right. And after that, he went to Taiwan.
Yes.
That's exactly about 4 years. And now he is in Chile, Universidade de Atacama. You have about 30, 40 minutes, okay?
Okay.
Thank you.
Thank you, Silvia. And again, thank you very much for inviting me. And sorry for last time about the earthquake. It was really unfortunate. But let's hope today there's no unexpected events. So I want to present today essentially the work we have been doing with a student, Sebastián Ramírez. Sebastián is from the Universidad Católica de Chile, so he's not in my university. He's doing the masters in Santiago, but when I first came to Chile, I actually arrived to Universidad Católica to work with Cristóbal Petrovich. But I was there just for a couple of months before coming here I was there as a postdoc, so then I came here as a faculty. So of course I took this position better, but I have continued working with Sebastián and with Cristóbal, and my long-term collaborators, Antonio Peinberg, and more recently, Ángeles Pérez Villegas from UNAM in Mexico. So this paper has not been published yet. The refereeing has been taking ages this time, unfortunately. So we decided to upload it to arXiv. And if you follow that link in the top left of the screen, you can go to the PDF of this paper. All this work has been done in a good load of the work has been done by Sebastián. In particular, all the numerical simulations have been done by Sebastián. He's pretty good for computer stuff, and he loves data and he loves big data. So he was very happy to work with Rebound in particular, and with all these sets of numerical data. It's been very satisfying working with him, and I hope he continues long time in planetary sciences. So okay. Last time I think I start with the introduction. I don't really remember how far I went, but I'm going.
I don't remember.
But I'm going to go over this quickly because also it's something probably familiar to many of us. The Kuiper belt and the structure of the Kuiper belt, which is the reservoir of short period comets beyond the orbit of Neptune. So anything with 30.1 astronomical units and above, it's considered a Trans-Neptunian object, in particular a Kuiper belt object, if they are in this main belt located between the 3.2 and 2.1 mean motion resonances of Neptune. So essentially, this Trans-Neptunian region we can classify it as the classical Kuiper belt, and there are subdivisions in the classical Kuiper belt, the cold classical Kuiper belt, hot classical Kuiper belt, inner classical Kuiper belt, outer classical. We have the kernel also in the cold population, but essentially is this what we would talk as the main component of this Trans-Neptunian region, this disk-like or ring-like component of all this Trans-Neptunian region. There is a very particular family of objects, the resonant populations, which are trapped in mean motion resonance with Neptune and constitute some of the best characterized examples, because it turns out that we can point surveys in the sky at particular locations and find resonant objects, because resonant objects are always going to get close to perihelia at particular locations in the sky. So it's easy, or it's surveys can target these objects in particular. So we can get large populations in these mean motion resonances, particularly in the 3-2, the one where Pluto is trapped, the Plutinus. Of course, we also have the scatter or scattering disk, which is formed by objects with larger eccentricities, larger inclinations, and that are being perturbed by Neptune. So essentially, the perihelia is around 30.1, and this is not set in stone. Many people can use different limits, but we can think it be below 38 astronomical units. An object can be considered to be in the scatter or scattering disk. If the object has a perihelia larger than this, it's essentially detached. It's not completely detached, but it's not being perturbed by Neptune or the giant planets currently. So in this region is the extreme Trans-Neptunian objects, and in particular the detached objects, the ones that are essentially fossilized there. They do not move. And it's actually pretty strange how they get there. One of the open questions in solar system science. Okay. And finally, we have the Oort cloud for objects with semi-major axis larger than 1,000 astronomical units, and we can divide that between the inner Oort cloud and the outer Oort cloud for things outside 10,000 astronomical units. So that's more or less the picture of the Trans-Neptunian region. We are particularly interested in the resonant populations in this work. So seeing the objects in the phase space of semi-major axis eccentricity.
Sorry to interrupt you. To me, it's only the first slide. Did you change it?
Yep.
Okay.
Unfortunately, there's no transition. Okay, but I will explain it this way. So yeah, we are particularly interested in the resonant populations, but if we plot these observed objects in the plane of semi-major axis eccentricity and semi-major axis inclination, the phase space, the typical phase space, we can recognize the different families. For example, here in green, it's the classical Kuiper belt between the resonance 3-2, where Pluto is located, and the resonance 2-1. These 3-2 objects are called Plutinos typically, and these objects in the 2-1 mean motion resonance are called Tutinos. So I'm going to start calling them that way in this presentation. But also we have other resonant families in higher order mean motion resonances farther away from Neptune. We also have Trojans, for example. So as I said, the objects with the small perihelia are considered in a scatter or scattering, and we can trace these lines of constant perihelia in the phase space of semi-major axis eccentricity. So anything above the lines has a smaller perihelia than the line. So this orange line at 40 more or less represents the threshold between something that is being perturbed and something that is not being perturbed. This is blurred. This is not. There's not a clear limit, but it's a broad approximation here. And what we can see very clearly is that the detached objects are here in this region with large major axis, large and large perihelia, and they basically are completely fossilized. They don't move by the influence of the giant planets. This collection of objects was obtained from the GPL's small body database earlier this year, and it's comprised by 6,005 objects. So that's more or less the number of objects we know in this region so far, and these objects should increase actually quite a lot with the LSST once LSST starts to provide the results from observations, probably next year. So we can, as I said, we can see the different populations, and if we paint the location of the mid-motion resonances, it's much more easier to recognize that there are clumps of particles trapped in those resonances. Some more important than others. The 3-2 is the most populated. The 2-1, it's actually quite important. 2 is not populated that much, and one would expect this resonance to be actually pretty dense in objects, but it's not. That it's probably due to an observational bias because these objects are farther away, or could be other thing. That's one of the interesting points we are trying to explore in this work. There are other resonances that you will not expect to be as populated as, for example, the 5-2, and it turns out that there's a lot of objects in that resonance, right? And typically, some large objects can be found in higher order resonances like 9-1, 10-1. There has been recent discoveries in high order mid-motion resonances. So, of course, this orbital distribution is not cold. This distribution is actually pretty dynamically hot, and this structure, okay, is not like one would imagine at the beginning in the 80s, for example, with the work of Julio Fernandez, who was thinking about a belt of low eccentricity, low inclination planetesimals that were essentially the reservoir of short period comets. Actually, this structure turned out to be very, very scattered, and if we observe the spatial distribution of these objects known today, in an edge view perspective, you can see that that this is actually puffy. Okay, it's not flat. It's not razor flat disk. It's a puffy structure, more like a donut than a ring. And on top of that, the discovery of objects with large inclinations is difficult because the surface in the sky that you need to cover to find objects with large inclination, it increases, of course. So most of the surveys focus on the ecliptic, and that's why we have more objects known with low inclinations than with large inclinations. So there is an increasing bias here for inclinations, for larger inclinations. This should appear as an animation. So I need this to read here. So what we know is that this orbital structure cannot be explained by the current configuration of the giant planets. Okay, if you will put only a cold disk there in the outer solar system and you will put the planets in their current orbits and you let that evolve for 4 billion years, you will not produce all this structure. It's essentially impossible. The only thing that we will observe would be some particles getting trapped in resonances, in mid-motion resonance, where they can increase their eccentricities by the chaotic evolution inside the resonance. But outside the resonances, everything just more or less remains as is. So in order to have all these eccentricities and all this large inclination, something else is needed, and that is the early migration of the giant planets. Okay, so models of the migration of Neptune currently favor this slow migration, which took around 10 million years, and a grainy migration, so produced by interactions of Neptune with the leftover planetesimals, but with large planetesimals, in such a way that if you interchange angular momentum with a large object, the jump in semi-major axis would be significant, and this migration outward is not smooth. It's not a smooth process, but a grainy process that is makes Neptune jump in all this in all its way out. And in particular, the Tutinos, the population of Tutinos, it's very important because they could contain very specific clues about the Neptune's early migration. There has been this series of works in the past about these constrainings, and we are also interested in this idea and this work, in particular, considering the additional perturbations of large planetesimals currently being in the Kuiper belt. So before that, brief reminding of resonant dynamics, which is just to remind the basic ideas of resonant object. We know that if an object is in resonance, in mean motion resonance with Neptune, in this case, the resonant angle called phi, it's going to be confined to a particular range of angles. I mean, this resonant angle is not going to cover all the possible range from 0 to 2 pi. It's going to be librating in a confined range, okay? And the amplitude of that libration, of those oscillations, is what is called the libration amplitude. We can understand that libration amplitude as this drifting of the orbit around the location of the pericenter of the object. So essentially, if we place ourselves in a rotating frame with the mean motion of Neptune, as seen here, what we will see is Neptune almost static, because we are seeing the solar system from the top, and rotating with mean motion, with the Neptune's mean motion. So Neptune would appear almost static, but not static because it has a small eccentricity. So still it moves a little bit around the perfect circular orbit. But the other objects, in particular, the resonant object, is going to get to the perihelia at specific locations determined by the resonant angle. Okay, and all these drifts in the location of the perihelia essentially explain, or essentially are related to the total libration amplitude of this resonant argument. The relation for any mean motion resonance is this one, though we can include other terms, for example, the bar P of Neptune and the longitude of ascending node of the object and the longitude of ascending node of Neptune, but this is the most typical angle that we are going to find librating, and not the other angles, except in very particular cases. This is an example for this object Gong 2007 OR10, which has this resonant angle 10 times the mean longitude of Gong, minus 3 times the mean longitude of Neptune, and minus 7 times the bar P of the TNO. So for the 3-2 and the 2-1 mean motion resonance in the co-rotation frame with Neptune, this is what we see from the top. In particular, here for Pluto, we can see that these two approximations to the perihelia allow Pluto to avoid always close encounters with Neptune. So that's why Neptune, and in particular the resonant objects, are or can be very, very stable. The configuration in the 2-1 mean motion resonance, it's also very particular. We have these two islands of for the perihelia of the object, one center 90 degrees ahead of Neptune, okay? And this is called the leading island. We have this other conjunction of the perihelia, 270 degrees from the mean longitude of Neptune, which is called the trailing island because it's essentially behind Neptune. If we see this from the top, Neptune would be moving in that direction if we stop the co-rotation. And then we have the symmetric island, which is essentially this one, and center objects in the symmetric island can have any location for the perihelia, but it is centered at 180 degrees. Okay, typically with large libration amplitudes. So yeah, we are interested in these angles for the 3-2 and for the 2-1. And as far as these angles are confined, are librating, we have objects in mean motion resonance. So why the 2-1 mean motion resonance is particularly important? That's because the populations trapped at different islands of libration may not be equal. Okay, so here in this classic work from Chang and Jordan, he found that according to the time it took for Neptune to migrate from approximately 20 astronomical units to approximately 30 astronomical units, the number of objects trapped in the leading and trailing islands could be very different. So if the migration of Neptune would be very quick, the trailing island would be overwhelmingly more populated than the leading island. But the slower the Neptune migration, in this case 10 million years, this asymmetry is less pronounced. Nowadays, in the observational sample, there's a small asymmetry in this island, and that's one of the clues to constrain the migration speed of Neptune. However, we actually don't know if that population in the 2-1 mean motion resonance has been fossilized after the end of the planetary migration. So we, in this work, we ask if this population is not fossilized, is not frozen in time, how much they have evolved, and in particular, how large Trans-Neptunian objects that we know are present in the Kuiper belt can affect this evolution, in particular this ratio between leading and trailing objects in the 2-1 population. So in order to explore this evolution, we took the observational sample from the GPL, a small body database, and we select the objects in the 3-2 mean motion resonance and the objects in the 2-1 mean motion resonance, and found from the observational sample 558 plutinos initially and 149 tutinos, just selecting a broad criteria in semi-major axis. At the beginning, we do not attempt to do a more fine or a finer classification. We just take a range in semi-major axis around the nominal location of the 3-2 and the 2-1 and see what we have. And this is the number that we obtain. Okay? To compare this observed population, we also use a theoretical population. And for this, we use the L7 model, which is the bias model that came out from the CFEPS survey of the Trans-Neptunian region, and it contains a larger population. For example, it contains 3,340 Plutinos and 871 Tutinos initially. So we do this because, in particular for the Tutinos, we have a small number of test particles to play with. So we try to include this population to compare and to have a better statistic. So here in the left panel, I'm showing our initial distribution of particles at time 0, essentially. So this is the 500 and something Plutinos and the 3,000 and something Plutinos from the L7. So L7 model particles are in gray, and the observational sample is shown in blue. And as I said, this is making no attempt to filter the particles by anything except the semi-major axis. So we make these cuts here in semi-major axis for the 3.2 and for the 2.1. So the population seem pretty different. In particular, here you can see that the 2.1 modeling in the L7 is very, very coarse. They just put a square there that reproduce more or less their observations once they apply all their biasing. But they actually make no claim that this would be a good representation of the 2.1 population dynamically. But still is good because we have a large number of particles there. Anyway, just integrating these samples under the perturbations of the giant planets and the sun only. Okay, we did this with the rebound code, and after 10 million years, the populations start to be sculpted by the giant planets in a way very similar to for example, the theoretical population in gray becomes much more similar to the observational sample. And here in this plot in the right, now we are doing a filtering considering only particles that have a librating angle either in the 3.2 or the 2.1 mean motion resonance. So all these particles are indeed librating during a period of 10 million years. Okay, more on that. The red dots here are the largest objects in the observational sample that we found librating in this after 10 million years. So essentially, we took the list and ordered that by absolute magnitude, and we took the smallest absolute magnitudes and assigned them mass following a procedure we did in a previous paper, and these objects are going to be used later to see how they perturb the evolution of the mean motion resonance in the 3.2 and 2.1. But initially, we don't consider them. We consider only the giant planets. So this is essentially our initial population, okay, for long-term integrations. So we integrate this population for 4 billion years to see how they evolve. We found that the sculpting is already in place after 10 million years. Not much is happening after that, except for a continuous leaking process, an erosion of these populations. And this is clearly seen, for example, in the red dots, because we had these 10 objects at the beginning. After 4 billion years, we only have three of them. But even without that, it's very clear that the population is decreasing in number as time goes by. Also, these lines, these dashed lines, are the medians of the population, the median semi-major axis for each population, the median eccentricity, the median inclinations, and we do them to compare the statistical properties of the samples. One of the differences seen here for the 3-2 mean motion resonance, the median of the theoretical population, the L7, is way above the median of the observational sample. But this could be only related to an observational bias, of course, because the observational sample is biased against finding objects with larger inclinations, but also probably an overshoot of the modeling of the population. So probably this line should be a little bit above and this line a little bit below to be consistent among each other, and not this line way below and or this one way above to match the other one. So it's a little bit from each way. And the same can be said about this population, but the numbers in the 2-1 mean motion resonance in the case of the observational sample is pretty small to make sound conclusions. So we take that with caution. And regarding the evolution of this trailing, leading, and symmetric island, we observe just a small change in the fractional significance of each island. And the most important change comes for the leading island that we can see here in the cumulative plots of libration center against the fraction of the population in that center. Here for the 2-1 and the observational sample, we see that the initial population actually increases a lot the fractional significance of the population. But this again comes together with a decrease in the general population of the resonance. So this has to be taken with caution, right? Anyway, it increases from 35% to 55%. This could indicate that there's actually an evolution of the fractional ratio between the leading and the trailing island. So therefore, it's likely, or it's a possibility, that this asymmetry that we observe today is not only imprinted by the migration, but also by the subsequent evolution of the solar system. So these results are for simulations that only include the giant planets. Then we include the 10 most massive Plutinos and the 10 most massive Tutinos, as I mentioned, assigning them corresponding mass following the procedure from our paper in 2019. As you can see, Pluto is the most massive object by far in this collection of 20 objects. And so one of the main results of this paper is the effect that these 10 objects do to the resonant populations. We show this in this plot of the cumulative fractions, which is equivalent to this one, but now including the massive objects in green and in yellow. We don't see really that many difference, except that when including the minor perturbers in the 2-1 resonance, and also Pluto, okay, the behavior of the leading island does not follow that of the case when only the giant planets are present in the simulation. So in this case, including dwarf planets, as we call them, there's not this strong change in the fractional significance of the leading island. So that's another indication that we have to take these results with caution because of the small statistic and the combined process of declining of the population in general. Some important point is that as we at the beginning would expect objects close to the or inside the tree-2 population only affecting the tree-2 population, and objects in the 2-1 population only affecting the 2-1 population. However, in one of our experiments, we could include Pluto together with the 2-1 massive objects, and that's where we discovered that Pluto actually has a strong influence on the 2-1 population. I will show that in a bit. But yeah, regarding the evolution of these 10 objects themselves, once they are considering as perturbers in the simulations, it's important in itself because even if these objects are small, their self-perturbations also can change their evolution. For example, when they are considered massless particles, like test particles, just considering the giant planets, all of them in the 3-2 resonance remain stable in the resonance without problems. But when we consider them massive, their self-perturbations can cause some of them to be ejected from the resonance, being more unstable. So in this case, we lost one at 1.6 gigayears. This is something that we observed also in previous papers. The case of the 2-1 mean motion resonance is a little bit more complex because when they are considered massless particles, we only have 3 objects that remain in resonance after 4 gigayears. But when we consider them massive, we actually have 6 objects, or 7 if you consider this recapture one, that remain resonant for the whole integration. So considering them massive actually increase their stability. And then including Pluto also, with the other 10 objects, change a little bit the results. In this case, only 5 objects remain resonant for the whole billion years. So of course, this is due to the chaotic nature of the problem, but in general, it's to be expected that objects, in particular in this of this size, will have an influence on the general evolution of the populations. We can see this more clearly in the leaking rates of the populations in the 3-2 and 2-1 mean motion resonance. So here I'm showing results in blue for the populations with only the giant planets, in this case, for the observed sample, the small body database, and for the theoretical sample, the L7 model. So when only the giant planets are considered, there's a leaking of particles, but it's small. Almost 80% of the population remains after 4 gigayears in the resonance. But if we include the dwarf planets, in this case, in the red line, it's only including Pluto, and in the orange one, including all the 10 Plutinos, the leaking rate of the population increases significantly. And in particular, the fraction of unstable objects also increases very importantly. So that means that Pluto, essentially Pluto, and not too much the other massive objects, strongly influences the evolution of the resonant particles. We can see the same in the theoretical population in the L7, this blue line, it's only including giant planets, and the red and orange, again, it's including Pluto and the massive Plutinus. By the way, here, the dashed lines are the exponential fittings to these leaking rates. And these exponential fittings are given by this equation here, where the particular numbers, NU is the fraction of unstable particles, and this NS is an offset of the exponential decay, because this is converging to a particular fraction that is the fraction of stable particles that are going to remain in resonance no matter what. Okay, no matter what perturbations, there's always a very, very stable fraction of the population that it's going to remain there forever. Among them, Pluto, for example. Pluto, it's super, super stable. In the 2-1 mean motion resonance, we observe something similar. We have the blue lines are only giant planets, and the red, it's including Pluto only. Okay, so the 2-1 population and Pluto, and the orange, it's including the massive Plutinus that essentially does nothing to the population, and the green one is the resonant Plutinus and Pluto. So it's easy to see that Pluto it's actually more important than the 10 massive Plutinus that we considered initially. Okay, this is a surprising result that Pluto is affecting the 2-1 population. This still needs to be explored in detail. These numbers show how the inclusion of the dwarf planets affect the unstable fractions in particular. You can see here that the unstable fraction goes from more or less 22% to 64%, right? So the leaking rate increases very importantly when we include the dwarf planets, and that's an effect that's a result that we highlight in this paper. The same thing happens for the Plutinus. That goes from 50% of unstable particles to 75%, for example, here. And again, Pluto is the dominant force behind this leaking process. To compare these results with some previous results, we used these fittings that were used by Greenstreet in 2015 to calculate the number of craters that will be observing in Pluto and Charon by New Horizons. They did a basic fitting to the leaking rate of the mean motion resonances based on works by Morbidelli in 1997 and Tiscareno and Malhotra. So they fit this decay with a power of the time B, where B it's 0.55 for the 3-2 mean motion resonance and 0.77 for the 2-1 mean motion resonance. So here, this fitting is shown in the black dashed line, and our fittings to our decays using the exponential fittings are shown in solid lines. In particular, the blue one when only the giant planets are considered, and the other colors indicate what other ingredients we are using, and this purple one indicates the fitting to the decay of the L7 population. So in this plot, what we can compare directly is the blue line to the black dash line. And we see that for the 2-1 mean motion resonance, this fitting is very good. It actually describes very well the behavior of the 2-1 population when only the giant planets are considered, but it fails when the dwarf planets are included. Essentially, we can observe that the dwarf planets increases the leaking rate of both resonances. And in the 3-2, the fitting is not very good. But but it is what it is. Okay. Yeah. So, in conclusion, we found that the 3-2 and 2-1 mid-motion resonance population shrink in the long term, and we feed this process by an exponential. So this is essentially an stochastic process that a random lead by random processes that has an offset. This is not going to tend to zero, but it's going to asymptotically approximate a fraction of the certain fraction that represents an intrinsically stable component in each resonance. The dwarf planets do not change this exponential behavior, but they change the intrinsic fractions of unstable and stable components. Unfortunately, we cannot establish if the asymmetry between the leading and trailing islands in the 2-1 mid-motion resonances is significant, the evolution that we observe, in a great part because our population is very limited. And we know there are, on one side, in the observational side, we know that there are biases in this population. And then in the theoretical side, we know that this 2-1 population is not done with all the care that we would like. To explore in more detail the evolution of this 2-1 population, we will need a better sample, probably something that comes from LSST or with new theoretical models. We are now exploring what we can use in the future to constrain better this evolution of this leading and trailing librators. And finally, Pluto continues to be to show its importance, and we find that most of the perturbations that we observe, both in the 3-2 and 2-1 mid-motion resonances, are produced by Pluto alone, besides the giant planets, of course. And the importance of Pluto for the 2-1 mid-motion resonance could be due to their mutual 4-3 mid-motion resonance. Because, of course, if the Pluto is in resonance with Neptune and the 2-1 is in resonance with Neptune, there's a inner resonance between Pluto and the Tutinos, and this could be the cause of the perturbations that we observe for the Tutino population. This is also something that we want to explore in future work, as long as Sebastian is available. So thank you very much, and please questions if you have.
Thank you, Marco. Now it's open to questions. Any question? I have one. I have two, I guess. Mm-hmm. How do you treat collisions? Is there collision?
No, not in this case. We use the Mercurius integrator in Rebound, which is analogous to Mercury, essentially. So it changes from the symplectic to, instead of bullish story, it changes to ES15 when there is a Clausen contour. And it resolves the Clausen contours, but we don't track the collisions with, for example, with dwarf planets or with the giant planets.
Yeah. Mm-hmm.
We lost, I'm sure we are losing some particles in that way, but I don't think that's main sink of particles in the simulations.
A small population that collide with massive bodies. And any more question? No, I will ask another one. I saw that some of them were ejected from the resonance and captured again. It's just one?
No, there are more. Here, here is the detail, because this is, for example, recapture here.
I didn't see. Okay.
This is
Recapture.
also recapture. And some are only kind of dropouts, like for example this one. It's not librating, but it's very close to the resonance still at the end of the simulation. So just the resonant angle is no longer librating, but it's very close to the resonance.
And what do you see in your results? You see that the angle is circulating and then it starts librating again when the object is captured.
Yeah, this object is very particular, 2014 DO. It's ejected quickly from the resonance, so in the first 10 million years, it's librating very nicely. At 20 million years, the resonant angle, it's circulating, and then it is recapture. I didn't put the detail here, but it takes a long time to be recaptured again. It takes giga years.
Okay. Okay.
Yeah, it happens.
Thank you. Okay, thank you. Any question? Other question? No? Thank you again, Marco. Very nice. And do you intend to send to another journal, to another periodic?
Yes, it's already sent to the astronomical journal.
Okay.
And it has been in referring for too long. I think this is the second round in referring. So together with last one, it's been almost 6 months in referring.
Oh,
it has been taking ages and ages.
No, too long.
So that's why we upload it to archive. So now you can find it on AstroPH if you follow this link.
QR code.
The QR code.
Thank you. Okay.